So we've talked about light. We've talked about the behavior of light and its various properties. What we want to talk about now is telescopes. And telescopes are one of the chief instruments that astronomers use to learn about the universe. We are going to break our telescopes up. And first we're going to talk about optical telescopes, and then we're going to talk about telescopes which encompass a greater range of wavelengths, such as gamma rays and infrared and ultraviolet, to learn about the universe. But first, let's learn about the optical telescopes, the telescopes which show us the light that we can perceive with our eyes. And the most basic of optical systems that we have at our disposal is actually our eyes. If we look at the human eye, it consists of a lens at the front, which is held by a series of muscles. Those muscles can be used to actually stretch the lens and alter its shape to bring objects into focus. Now, this lens will use the principle of refraction to bend the light to a sharp focal point, where the optic nerve then takes that particular light data and transfers it to the brain and forms an image. And for thousands of years, this was the chief method of observing the stars. Here you have Tycho Brahe looking at the position of a star and recording its position visually without the aid of lenses or mirrors. And actual research into optical devices and using them to magnify images of both the sky and just faraway objects is very complicated, and people have been experimenting with lenses for a very long time, and eventually the telescope was born, as we discussed briefly when we looked at Galileo. Some of the earliest work into looking at systems of lenses actually comes from Roger Bacon in his Opus Majus of 1267. And he was actually looking at the sky and said that new stars appeared where there appeared to be empty sky when he put his system onto the sky. So here we have an armillary sphere here. This is essentially the celestial sphere looking at the stars. And Bacon put two lenses together. Some people claim that Bacon should really be credited with having invented a type of telescope. So he would use this system of two lenses, rather open, just with a large objective lens at the front and a small lens at the back, place it over the sky, and he would see brand new stars appear he couldn't see with his naked eye. Bacon himself was a little bit of a rogue where the church was concerned, and was often causing a lot of trouble to the establishment, and was actually imprisoned at some points in his life due to his views on philosophy and astrology. He was also one of the first people in Europe to formulate gunpowder. So, all in all, another one of these people with a bit of a turbulent history, but actually that contributed to science quite heavily. And there's some of Bacon's work. But systems of lenses have been used for a very, very long time. No one's really sure who invented the original telescope. And systems of lenses have been in use, as I say, for thousands of years. The first eyeglasses ever recorded were about 1290. Reading stones actually stretch back further than this. These were transparent pieces of quartz, transparent pieces of stone, which were shaped to allow magnification, and people would actually take these and run them over print and could actually use them to magnify print as a form of primitive magnifying glass. It's known that Cardinal Hugh of St. Char used actual eyeglasses, and there's depictions of him wearing eyeglasses as early as 1352. Nero in 54 AD did use a system of basic eyeglasses and lenses. This is quite a long time ago, and if Nero was actually capable of using these things and had them at his disposal, it's likely that others did too. So magnifying light with lenses was not a new idea. Leonardo da Vinci used water-filled crystals and lenses to actually put them together in combinations to magnify the moon. He also came up with a way of magnifying light and improving people's vision using a system of water and looking at the refractive index of water. Da Vinci also put his lenses onto the moon and described detail on the darker part of the moon's phase. So people were experimenting extensively with lenses before an actual telescope in the modern definition was truly claimed to have been invented. The first time someone actually tried to claim invention of a telescope was actually Hans Lippershey, who was actually in here's an actual image of Lippershey himself, and he was actually in Sweden, and he came up with what he referred to as Lippershey's looker, which could magnify objects by 3 times. And he actually applied for a patent here in the Netherlands in 1608. Unfortunately, it was actually claimed by other opticians and lens grinders that they had invented this telescope. So, consequently, Mr. Hans Lippershey was denied his particular application for the invention of the telescope, so the patent was not granted. And this is where people such as Galileo, hearing about Lippershey's work, started to build their own devices. For Lippershey's work, he is credited with a crater on the moon and a minor planetary body, an asteroid 31338 Lippershey. In other works, Ad-Din Muhammad ibn Maruf here, actually in 1526 to 1585, had published a book, say the Book of the Light of the Pupil Vision and the Light of the Truth of the Sights, a very concise title here, which described a long-distance magnifying glass, a long-distance magnifying device. Unfortunately, the observatory that Ibn Maruf was actually working at was in Turkey and was destroyed very, very quickly and did not last long. But at the time, it was considered to be the most technologically advanced observatory ever created. So devices were being used to look at the stars, and many people can claim that they invented an optical device, if not a telescope. One of the people who claims this is Thomas Digges, who created something called a perspective glass in 1571. Astronomer Thomas Harriot actually carried one to Virginia in 1585 to observe an eclipse. So it's possible that a telescope was already present in the Americas before Galileo made his historic observations. This system actually used a lens and a mirror. This is a reflecting telescope, as opposed to a refracting telescope that Galileo had constructed. It's also possible that more was not made of this particular telescope because it was considered to be a military secret. Leonard, Thomas Digges' father, worked with Thomas to develop a telescope, and they actually published this work in a paper called Pantometria here, and here's a model of their telescope on a very modern tripod, of course. And you would have a reflecting mirror at the back and a lens at the front here. And he described this fair seeing glass in the 1500s. Thomas Digges was also one of the people to point out something called the dark sky paradox that we'll talk about later, as to why, when there's stars all over the universe, is the sky actually dark? But Thomas Digges and Leonard Digges, of course, created some kind of telescope and was definitely used around the time of the Spanish Armada invading England. Queen Elizabeth of England had a very advanced system of intelligence and was one of the first people to employ an actual organized secret service, and had a secret weapons program that was actually in place. And it's thought Diggs was actually developing optical devices for the Crown to be used in this secret war. So Queen Elizabeth at some point actually rewards Diggs with a lot of land and a lot of money for unspecified services to the Crown. So it's quite possible that Thomas Diggs actually gave his telescope to the British government so that they could use it to see ships coming and prepare themselves for attack. And there's Queen Elizabeth after the defeat of the Spanish Armada, which may possibly have been due to one of Diggs's inventions. Diggs's telescope would have been a box of this particular description with a lens at the front and a reflecting mirror here, which would have formed an image on a screen, very much like a monitor that could be used to point out to sea or point across land and form an image. This would have been a rather large device and would have been a very difficult thing to have used aboard a ship, whereas a modern telescope used aboard ship would have been essentially a tube with two lenses in it, which would have been much more portable and much easier to employ. Of course, as we've discussed before, Galileo had heard of Lippershey's invention, his looker, and the inventions of others, and wanted his own telescope. He had a lot of difficulty attempting to acquire one. In the particular region he was living in, he could not actually obtain a telescope. So he obtained the lenses that he needed for a telescope, built the tube by calculating the correct focal length, and just constructed his own particular optical device. And of course, Galileo made his famous observations of things like features on the moon, and published his Sidereus Nuncius talking about the evidence for the heliocentric system, as we've discussed before. And of course, even though Galileo did not necessarily invent the telescope, and we cannot directly credit him with that, we can credit Galileo with publishing the first scientific paper containing works from telescope observations. When we talk about telescopes, there are many different types of telescopes. The two main ones are refractors and reflectors, and there is a subtype of the reflector called a catadioptric or a Schmidt-Cassegrain type of telescope, which uses a bit of refraction as well. But the two basic types are refractors and reflectors. And here's how they really work. With a refractor, light comes in through a lens at the front of the tube and is bent and brought to a sharp focus here, where an eyepiece is introduced, which refracts the light again, and by using different combinations of eyepiece with front lens, you can actually magnify light. There's also a reflecting telescope. Here, light comes in, hits a shaped mirror, which magnifies the light, bounces it back to a flat mirror, which then bounces the light to an eyepiece and then magnifies it further, allowing the viewer to have a better view of the object of interest. The third type I mentioned, which is a subset of the reflecting telescope, is the catadioptric telescope, and this essentially is a Schmidt-Cassegrain, the type of telescope we have here. And light here runs through this front correction plate, through this refracting plate, onto this mirror. This mirror then creates the magnification necessary, bounces the light back to a flat mirror, which then bounces the light again into an eyepiece. This has some advantages in design over this Newtonian type of reflecting telescope. So we talked about refraction before, but just as a recap, refraction is the bending of light as it passes through a lens. Light is moving fast through vacuum, then moves through an atmosphere and slows down, it'll move through air, and then as it enters glass, it will bend again as its speed is changed. This means that if we put different types of glass together, we can bend light as much as we wish to put it in the position that we wish and magnify it. You don't need to know Snell's law as such, but this is the scientific law that actually determines how much light will be bent by different densities of material. So here's light coming in at an angle to this piece of glass. As it travels into the piece of glass, it will move at a different angle in the glass to the air. And that's the principle of refraction. And this is why when we look at, say, this pencil in a jug of water, it looks like it's broken. That's because the light coming through the water and the glass combined will be coming to your eye at a different angle to the light from the pencil just in the air. It's not that the pencil is actually broken, just the light is coming from different angles. And that's what you're doing when you look at a refracting telescope. So here is a typical kind of telescope with a lens at the front, light is coming in, being bent or refracted as its speed is changed, and brought to a sharp focus. It's then refracted again, and the different combinations of eyepiece and size of front lens will allow different magnifications to be achieved and bring the light to a sharp focus. There is a little bit of a complication here with refracting telescopes, and that's something called focal length. Now, the bigger you make this lens here, the longer this distance between the point where the light comes to a sharp focus and the lens is. So if this was an even bigger lens, the point where the light comes to sharp focus would be over here somewhere. And that means if you build a really big refractor like this one, which has an enormous lens in the front, that means you have to have a very long focal length to bring the light to a sharp focus. And that means refracting telescopes like this one shown here get to be very, very long and very difficult to manage. So it's not the size of the lens so much as the infrastructure needed to build a very large refractor. Look at the size of this dome compared to these people and how heavy this particular mount has to be to hold this telescope. And that's a lot of weight of glass at the front of this telescope as well. So there's a couple of disadvantages to the refractor. One is very big refractors need to have all of this infrastructure to make them work. Refractors and Cassegrain telescopes also give you an upside down image unless you correct them. It's easily corrected with another mirror, but that means introducing another mirror to your optical device. So refracting telescopes will often give you an upside down image, or it will be the right way up, or will be reversed from left to right. So if we pick on the Pleiades, the little collection of stars in the constellation of Taurus, if you were to look at them with your eyes, this is what you would see. The Pleiades are often called the Seven Sisters because there are 7 stars in this little formation. I think you can see about 5 with my eyes. Now, if we are to look at an inverted image, then you would look through the telescope and you would see the Pleiades upside down. So a typical refractor without a mirror in it would give you this effect. Depending on the orientation of the system and how it's configured, you might also see, instead of an upside down image, a left to right reversed image. So sometimes this can be difficult for people to involve themselves with telescopes when navigating around the sky is either inverted and upside down or is reversed left to right. And that's something to be aware of when looking through an optical device. Is it as you see with your eyes, or has it been changed by the optical device itself? So as I said, refractors can get very big if you're going to build very large systems to magnify your light a lot. And consequently, most systems used in modern astronomical research are not refracting in type. Also, if you go and buy a very cheap refracting telescope, often if you go to one of these stores at the mall during Christmas or something like that and purchase a telescope from them, you will often find that turning it on, say, a blue star or even just a source of light will result in all of these colored images. And all of those colors actually come from an effect called aberration. And this means that not all of the wavelengths of light are coming to a sharp focus. And while this may be pretty, it's actually corrupting the image of the object you're looking at. So poorly made lenses give you this aberration effect. Here's what our star should look like, a nice sharp pinpoint of light, but when you look through a very poorly made lens, you end up with this kind of smear of different colors. So what alternative do you have to the refracting telescope? Well, the alternative is to use reflection. Use a shape mirror to actually magnify your light. And of course, with reflection, light comes in, bounces off a mirror, and then bounces off at another angle. And that angle that it bounces off will be equal to the angle that it's incident. The history of the reflecting telescope is a little better documented. Zucchi in 1630 actually came up with a type of reflecting telescope. Christian Huygens, who had a space probe named for him because of his observations of Saturn, built a better eyepiece for this system in about 1650. Newton also invented his own type of reflector about 15 years later or so than Zucchi did. Well, about 30 years later. Cassegrain, the type of telescope that we have here that now bears his name, the Schmidt-Cassegrain system, also invented his type of reflector. And Robert Hooke, who we talked about before in his battles with Newton, invented his own type of telescope called the Gregorian telescope. But mirrors have been in use for a very long time. It's thought that a mirror that was extremely large was constructed by the Roman Empire to put in the lighthouse at Alexandria so that light could be beamed further out into the ocean to actually navigate shipping. And this lighthouse is one of the 7 wonders of the ancient world and contained what may have been one of the largest mirrors of the day. Newton, as we discussed before, invented his own type of reflecting telescope with this very complicated kind of ball mount. But essentially, here's his mirror at the back, light would come in, bounce off, and then be bounced back upwards, reflected upwards, to a flat, as it's called, a flat mirror, which would then bounce the light through the side and into the viewer's eye. This could be focused by actually moving this tube in and out. And that's the type of reflector that bears his name, the Newtonian reflector. And as I said, here you have a tube, you have a shaped mirror, you have a second mirror and an eyepiece. Light comes in, bounces off of this mirror, is focused onto this flat, and then bounced through the eyepiece to the viewer's eye. And there's a typical modern Newtonian reflector, here with a computer control system. The Newtonian system actually produces an image again which is upside down. So not particularly useful for land use. If you want to look at a person or bird watch, everything will be upside down. And it's a little difficult to correct. It does mean putting extra lenses and mirrors into the system, which will reduce the brightness of your image, which, while maybe not a problem if you want to look at a local woodpecker, may be more of an inconvenience if you're looking at something like a very dim star. So quite often what astronomers would do if they were using this type of telescope, which was actually very effective, is just turn their star chart or their map upside down to actually show what they were seeing through the telescope. So here we have Hubble images of Mars, how Mars actually looks, and here is the equivalent earlier map from Antoniadi's observations of Mars, an astronomer who made very good observations of Mars. We'll talk about some of these straight lines that actually don't exist later on in our discussion of Mars itself. But here you can see various features on the surface of Mars. Here's the Hellas Basin, here it is in the telescope, and as you can see, all of his maps were inverted, so they actually matched his view in the telescope. So in terms of Newtonian telescopes, they had some advantages. You can build a large telescope quite cheaply. They're relatively easy to make, and you don't have so much glass in them blocking and scattering light as you do in a refracting telescope. There are some disadvantages, however. The eyepiece can often get very high off of the ground, and you often require some kind of ladder to actually climb up and look through it. There's sometimes if you are not mounting your mirror properly, you may see some image distortion. And a bigger disadvantage is that these mirrors actually kind of oxidize, a type of rust which dulls them with age and takes away their reflectivity. Mounting a telescope was also something of a challenge in the early days, and as you can see, this telescope cannot point left or right and is actually just mounted on two blocks. This is an 1873 transit telescope, and you have to wait for the right time of night for your object to be right in front of the telescope and transit across your position on your meridian. So there were some engineering challenges in the early days of telescopes and pointing them in the right direction. But the modern telescope, such as the type we have here, is a reflecting telescope, and it really uses the shaped mirror, as we said, and the Schmidt-Cassegrain tends to be a rather popular choice in the modern world. Here, light is coming down through the tube, bouncing off of the primary mirror at the rear, bouncing forwards, hitting the secondary mirror, and then being bounced through a hole in the mirror to a focal point. And most research telescopes today are of this kind of type. And there's a Schmidt-Cassegrain telescope, a rather large one on fork mounts using ALTAZ, altitude and azimuth coordinates, which now we have computer control, are a lot easier to do. Light coming in, bouncing off of the shaped mirror, flat mirror, and then through this eyepiece at the back. This small telescope here, which people often look through mistakenly, is actually a finder scope. The field of view when you have a very high magnification is very small, so you don't see a lot of the sky through this eyepiece. This telescope has a wider field of view and actually enables you to find objects much more easily. If you were to look through this telescope, you'd look through here. So why do we even build big telescopes? Well, the bigger the telescope, the bigger the light collecting area. A bigger telescope is essentially a bigger light bucket. It's collecting more photons from your object and giving you more detail. So it gives you more light than your eyes can see. And that means we get more what we call resolution. We can see smaller and smaller objects on the surface of the thing we're interested in looking at. So look at a planet, you can see greater and greater detail. Even if you put it on the sun, you should see more detail in the atmosphere of the sun than you could with a smaller telescope. And we can add instruments to the back, so we can actually detect light that's invisible to our eyes in the infrared and the ultraviolet parts of the spectrum. The largest optical telescope that's actually in operation today is in the Canary Islands, the Gran Telescopio Canarias, at 34 feet across in mirror size. And there it is above the clouds at its location on top of an extinct volcano. So this mirror here measures 34 feet. Historically, a telescope referred to as Lord Rosse's Leviathan was constructed as early as 1845, and this had all of the problems that I've discussed before. This is a typical reflecting telescope, 72 inches across, which for the time was enormous. And Lord Rosse was a aristocrat living in Northern Ireland. And as you can see, there's a lot of ropes and a lot of attachments all over this telescope. And the telescope is also open to the air, which is a bit of an inconvenience. And while observing, Lord Rosse would have to pick up this telescope and sit in a basket up here to look through the side of this, through the eyepiece. So by pick up, I mean they would have to actually manipulate this complicated series of wires and masses and blocks and weights to actually lift this telescope up. And as you can see, the ladders here are quite precarious. This would not be a particularly nice telescope to be using in the pitch darkness on a particular winter night, but you would have to be elevated quite high to look through this eyepiece. This was actually a very effective telescope, but unfortunately the actual logistics of using it presented some dangers. So sizes of telescopes really matter. They give you a large light collecting area if you have a much bigger telescope, and that better angular resolution that I was talking about. So a larger telescope size allows you to see fainter objects. And here is the new telescope that has been suggested for Mauna Kea in Hawaii in 2020. This was supposed to be constructed but has been delayed through various political and coronavirus effects. And this will actually have a sort of iris here that will open up as opposed to a typical dome that we see with two big shutters. And this will be the 30-meter telescope. Just for comparison, here's the various sizes of telescopes from about the 1800s all the way up to the modern era. At the bottom here we have a tennis court and a basketball court for scale. Over here you can see a lens which was constructed for the Great Paris Exhibition telescope in 1900, relatively small. The Yerkes Observatory, this was at one point a refractor which was one of the biggest research telescopes available. You can see 40 inches. These lenses and these mirrors are all essentially one piece. Eventually a lens or mirror gets too big and too heavy, and so that means you have to start building segmented mirrors. That means lots of little mirrors put together to arrange for one mirror. So this is one mirror essentially made up of multiple little reflective hexagons. And as you can see, the sizes are generally increasing. The largest telescope I've managed to get my hands on is the Keck telescope, Mauna Kea in Hawaii, constructed in the mid-90s. And this is actually comprised of two telescopes, of which the signal is combined to simulate a much bigger telescope. Future telescopes are such objects as the 30-meter telescope planned for Hawaii, or the Chilean European extremely large telescope. There's an imaginative name. And here's a human scaled to these various reflecting telescopes. So this is an enormous mirror made up of all these little reflective hexagons. The overwhelmingly large telescope, as it's so aptly named, would have been twice the size of this, but that has since been cancelled. The James Webb Telescope, which is the replacement for the Hubble Space Telescope, looks like this. So you can see space telescopes are actually better because they are above the atmosphere, but they are relatively small in diameter compared to Earth-based telescopes due to the fact they have to be launched into space on a rocket or space shuttle vehicle. Just for reference size, the Arecibo radio telescope is this particular great big circle here. So radio telescopes tend to be relatively low resolution and have to be huge to gain any decent images of the stars or planets. We've talked about angular resolution several times. But what do we actually mean by that? Well, this is the smallest separation between two objects that you can determine through your telescope. And to really understand what we mean by this, if you stand outside at night, please don't stand in the road at night. This would probably result in injury. But if you were to watch a car at a very long distance, you may see a single light. You'll not be able to resolve that separate the two headlights of the car at very long distances. As the car gets closer and closer, you'll see the angular separation of these two lights. So angular resolution is the minimum separation between two objects that you can distinguish in your telescope. So here we know that these rail lines are the same distance apart all the way along. If these were a meter apart, they'd be a meter apart here and here and here and even off in the distance. But to your eye, the angular resolution makes it look like these two rail lines are meeting in the distance. So angular resolution is the smallest object that you can discern. So double stars are a great test of this with a telescope. These are two stars that are very close in space and essentially look like one object. So at low resolution, you might see this weird egg-shaped thing. At a medium resolution, you might see something that's a bit of a figure eight. Increase your resolution now to high resolution, and you might actually resolve two objects. Think back to Galileo and his weird Saturn with cup handles on the side. Now, a modern telescope will clearly show you that that is a planet with rings around it. And here's an image of the Gemini North telescope, 8 meters across. And the Keck 1 and Keck 2 telescope, these are 10 meters across, but can actually be linked together to simulate a much bigger telescope. The Keck telescope is about the second and maybe third biggest in the world at this point. And they actually use a system that's referred to as adaptive optics. Now, adaptive optics are a system whereby you can simulate the turbulence of the atmosphere and actually screen it out. So temperature fluctuations, as we said with twinkling stars, can actually cause atmospheric turbulence, and that will distort your image of the sky. As we try to bring the light to a focus, it will blur it just a little bit, and that actually means it will be blurred a lot with something like a 10-meter telescope. Consequently, we can take a laser and we can shine it through the atmosphere and we can create an artificial star. And from that artificial star, we can then deform the mirror to match the atmosphere, and we can screen out the effects of the atmosphere and essentially correct for what the atmosphere is doing to our image of a star. So we actually have mirrors with lots of little pistons behind them. Light comes in, our image of our guide star, the star that we're creating with a laser, will then be used to see how much the light is distorted, and then we can distort the mirror to account for this effect using these little pistons. And here's what the back of such a mirror would look like. And we can take a single sheet mirror and we can deform that, or we can use lots of little mirrors and move those around, similar to the system used on the Keck telescope. So this is a 10-meter telescope made up of lots of little hexagons which can be individually moved to account for atmospheric effects. And as I said, this is the largest telescope I've managed to utilize in my life. And here's an actual operator, a technician sitting in the telescope working on the optics. As an observer, you get to stay down by the ocean in Hawaii and operate this telescope from there. So we shine a laser and create an artificial star 95 kilometers up in the atmosphere, and then deform our mirror to match whatever that star is doing, since we know how that artificial star should behave. And there's Keck with the laser guide star. So this huge beam can often be seen on long time-lapse photography coming out of the top of the telescope. And here is another telescope, the Infrared Telescope Facility, another facility I know well. This facility over here is the Subaru, or a Japanese-funded telescope. And here's a comparison of what happens with and without adaptive optics. Without adaptive optics, you might see two blobs. With, you can actually get detail in the atmosphere of Jupiter. Here's an image from Keck of Io, a moon of Jupiter. This is from the Voyager 1 probe, which did a close pass to the actual planet itself. And here's the adaptive optics of the Keck telescope from Earth in about the same wavelength, showing us very similar detail. So this is very impressive for the size of the object to get an image this accurate. And there are many examples of what adaptive optics can do. Here we can see without adaptive optics, this is one blob. If we actually use adaptive optics, we can see there's actually three individual objects here in this system. And again, in looking at planets, without adaptive optics, we essentially get two blobs of detail. With, we can actually see detail in the atmosphere of Neptune. The human eye is actually an adaptive optics system, and adaptive optics are extensively used in surgery and ophthalmic treatments and have a lot of military applications. But there's one thing that we haven't discussed yet. Well, we've touched on it, but really does not sit well with Earth-based telescopes, and that's the weather. So here's Keck in the snow, and yours truly was given about 7 nights of observations to make with this telescope. So here's Mauna Kea in Hawaii in February 2008, and at the peak of this volcano it is snowing. And this weather system wiped out an entire week's observations. And this is a serious problem with ground-based telescopes. Sometimes the weather just becomes so severe that you can't do any observations and have to just go and play in the snow, or put snow tires on your car in Hawaii. Yes, I'm still bitter. And the only way to get around this is to really just put a telescope in space. And the Hubble Space Telescope has been the most successful space telescope ever launched. And this is in the optical wavelengths, the wavelengths that you can see with your eyes. But the great part about the Hubble Space Telescope is it's above the atmosphere. There's no interference from the snow or the rain or any weather whatsoever. So you can actually get much better results from a small space telescope than you can from these very, very large ground-based telescopes. Unfortunately, the Hubble Space Telescope is now getting decades old and has had at least one servicing mission. Currently, there is no spacecraft capable of servicing the Hubble Space Telescope to keep it running for much longer. And so, a replacement, the James Webb Space Telescope, has been put together. Its launch date was originally March 2021. I do not know if this has been put back, but the James Webb Space Telescope, named for the former administrator of NASA during the early days of manned spaceflight, is actually quite an ambitious project and costs about $10 billion in about 2016, not adjusted for inflation. And here's its size. Here's an astronomer of about 2 meters high. There's the Hubble mirror at 2.4 meters. And there will be the size of the Webb mirror at 6.5. And once again, we're now looking at, instead of one mirror, we're looking at a segmented hexagonal mirror made up of lots of smaller mirrors. And the James Webb Space Telescope will be deployed. It has a big thermal shield, that's this foil thing at the bottom that's currently unfurling, that will be pointed towards the sun to protect it from high intensity radiation. The telescope itself, once deployed, will actually have to unfurl this big solar shield, like so. It will then have to deploy its various mirrors after exiting its parent spacecraft. There we go. Mirrors in place, ready to observe. And this spacecraft is being sent a long way out. This is going out to what we call the Lagrange point, L2, a stable point in Earth's in the orbit of the Earth during its cycle around the Sun. So here we have the Hubble Space Telescope at 570 kilometers. Here's the Moon at 384,000 kilometers. And here's the Webb Space Telescope going out to L2 at 1.5 million kilometers. So it will be orbiting the Earth very far away and following the Earth in its orbit at what we call the Lagrange point. Of course, there's a big disadvantage here. At 1.5 million kilometers, if something fails on this telescope, there's no mission to rescue it. If something fails, we will not be able to go and put this telescope back together and repair it. As you can see, its orbit will be quite odd. So one of the really useful things about space telescopes is they are above the atmosphere. Most of the electromagnetic spectrum, including all of the ultraviolet and X-ray radiation, will be absorbed by the atmosphere. This is good for us at the surface of the Earth because it means we're not irradiated and given cancers, and life on Earth is not affected by this extreme radiation. But it's bad from an astronomical point of view because all of this information is essentially lost. Gamma rays through X-rays, most ultraviolet. Now, if we go to very high altitudes, we can pick up some infrared radiation, but it's only really the visible radiation and radio waves that make it down to the ground. And as such, that's why we're so limited in terms of the amount of astronomical work we can do from the Earth. There have been gamma ray telescopes and X-ray telescopes which have to be in space to actually receive these wavelengths. Hubble is a visible telescope, and in Spitzer and WMAP these are infrared and radio telescopes and microwave telescopes. One of the things that should be pointed out at this point is the James Webb Space Telescope is actually in the infrared. It's seeing the heat radiation of objects in the universe. When Hubble goes offline, you will no longer have a space telescope that will give us images that you would see with your eyes. All images that we will have will be what are called false color. Colors will be assigned based on brightnesses, and that will tell us how these objects look at their heat wavelengths. So consequently, we will not have anything in space that will tell us how an object would look to the human eye. So as we've said, turbulence causes twinkling. Stars from space will be much better than stars from a ground-based telescope. Here you can see the atmospheric distortion that has caused this image to become rather blurred. From space, Hubble can see a very coherent star. Other problems are things like light pollution. To go outside and look at the stars, now with all of the lights from modern society, this light is actually blanking out the stars for a huge proportion of the populace. It's only far more remote parts of the planet where we can see truly dark skies. And this means that viewing from these locations is getting progressively worse. If you go outside on a particularly cloudy night, you might see a red or yellow tinge to the clouds. That is actually a result of light pollution, light from the cities reflecting back off the clouds. So in terms of space telescopes, an advantage of a space telescope is there's a little light pollution or turbulence in the atmosphere to affect your image. It solves the atmospheric absorption of light, meaning that X-ray telescopes and gamma-ray astronomy can be done from orbit that can't be done from the surface of the Earth. Some disadvantages? With something like Hubble, the Moon and the Earth still shine into its aperture and actually cause interference from very faint objects. Not a problem with the James Webb Telescope. But what is a problem with both Hubble and the Webb Telescope is that it will be hard to service. If something goes wrong with a telescope in orbit or out at L2 as Webb is, they will be very hard to fix. And Hubble has already had one servicing mission to fix a major flaw. A good solution is putting telescopes on the moon. When people return to the moon and are exploring the moon, to put them on the far side of the moon where there's little interference from the lights of humanity and the shine from the Earth. This will actually enable us to create telescopes that can be serviced, that can be visited, and with modern robotics, possibly even completely used completely remotely.